Greetings everyone, Dr. D here. Let's talk about Chapter 2. So moving on now to the first physics chapter of the book, we've got two major concepts. The first half is precise words, speed, velocity, acceleration, displacement, the words that we use to describe where things are and how things are moving. Then we're going to relate those variables with equations. We'll call these the big four equations. They talk about how things move. We haven't yet explained why things move, but we're going to be using these quite a lot this semester. They're going to be important for us. So let's dig in. The first definition is just speed, and like you've known for a long time, you take distance equals rate times time, or rate equals distance divided by time. That's it. That's the only concept there. So if I take the distance traveled over how long it took, that would give me an average speed over the entire trip. Since the SI unit for distance is meters and time is seconds, my SI speed is meters per second. But now let's talk about how we do this with vectors. So first off, let's define displacement. I'm going to take an object that starts at some position, and I'm going to use a vector to define where it starts. So the book calls this x0, its initial position at time t equals 0. So then the object moves, ends up at vector x as its final position. And the difference, final minus initial, is just the displacement. So the x vector, the displacement vector, is always referring to how far the object has gone from its original position over some amount of time. So, quick example just to try to clarify things. If I start on the left and end on the right, and I travel on the red line, that's the distance. How many meters have I gone? The displacement is just the final minus initial positions. The displacement depends on the separation from the start and end points, and how far I actually traveled is completely irrelevant to that. So if I'm going to have displacement, I have to move. If I'm moving, that means my position is changing, and so that's the very definition of velocity. If I have some displacement that's not zero, the amount of time that it took me to do that, I divide displacement by time and I get a velocity. So like you're used to, miles per hour or meters per second, I take a displacement in meters divided by a time in second, and I define a way of changing position. So remember now that this is a vector, just like displacement is a vector, so it has a direction. My velocity is 10 meters per second to the right, or up, or north. And those directions are going to be really important for us mathematically. The definitions are the same as with the scalar quantities, speed and distance, but we now have directions to worry about. So to clarify, distance and speed are scalars. Displacement and velocity are vectors. Paying attention to the units makes everything easy. So if I have an object that's moving, it's got some kind of velocity. If the velocity is changing, then I have an acceleration. So let's think about this for a little bit. Suppose I have a constant velocity. My car is moving at a constant speed of 60 miles per hour, and that velocity never changes. Well, my object is moving very quickly, but there would be no acceleration. Acceleration is when I change my velocity to a different velocity. So if I start at 0 and then I end up going 60 miles per hour later, that's an acceleration. So the acceleration measures how did my velocity, which is measured in meters per second, change over several seconds. So it's meters per second, or meters per second squared. A is the change in velocity over a change in time. So what we can do is we can define 5 variables, and these are our kinematic variables, the variables of motion, how things move. Displacement, x, acceleration, a, and we're going to assume that acceleration is constant, it's not changing. but I do have an initial velocity and a final velocity over some time t. What I need to do now is take these 5 variables and use equations. So these are the big 4 equations that relate them. Let's dig in here and talk about these for a second. So equation number 1, this top one, v is v naught plus at. This is from the definition of acceleration. What this says is that acceleration makes the velocity change. So if I were to start at some velocity v naught, and I'm accelerating for some acceleration a over some time t, my final velocity v is different from v naught somehow. So equation 1 says, how does acceleration affect velocity? Equation number 2 is just a definition based on average velocity, distance, and time. You know, the average between any two numbers, I add them up and I divide by 2. So the initial velocity plus the final velocity divided by 2, that's just the average velocity. Displacement x equals average velocity times time. Just like you know, distance equals rate times time. That's the concept there. So how does average velocity affect my displacement x? The third equation says, how does acceleration affect my displacement x? So x equals v naught t, kind of like distance is rate times time, but now I have this other term for how the acceleration affects things. These equations are really easy to remember if you pay attention to units. So x has units of meters, meters per second times second has units of meters, 1/2 has no units, but meters per second squared times second squared equals meters. So units of meters, units of meters, units of meters. The fourth equation is the one that doesn't have time in it. So I'm relating now final velocity and initial velocity to acceleration. So again, how does acceleration over a distance affect my velocity? You're going to want to keep these handy. You don't need to memorize them, but have them written down somewhere accessible because we're going to be using these quite a lot. So 2 examples, and then we'll wrap this up. So example 5 from the book. Let's take a look at the situation and then how we solve every single one of these problems. The absolute best thing to do is to draw a picture. You don't have to involve clocks or anything fancy, but just a note of where you're starting, where you're finishing, and what you know. The absolute most important first step is to write down what you know and do that while you are reading the question. So I'm going to put up a little table here, and let's keep track of things as we read the question, because I'd be writing these down with my pencil. So a speedboat has constant acceleration of +2 meters per second squared. So I'd write down a equals +2. If the initial velocity is +6, so v naught is +6, find the boat's displacement, so I'm finding x, after my time is 8 seconds. So I know a, v naught, and t. I'm trying to find x, and we haven't said anything about final velocity. So now I would go to my big 4, and I'd figure out which equation do I want to use. So here's my 4 choices from the last slide. I would want one that has x, a, v naught, and t in it. So let's take a look. Which equation do I want to have? Not this one, but this third equation. That looks like the right one. All right, so now let's actually solve the problem. Okay, so I'm going to take my third equation, the one that relates all the variables that I want, and now I'm going to solve it for x. Well, looks like I'm already done there. So I'm trying to find displacement. I need to solve for x. It's already written that way, so we're great. Now I'm just going to write down the equation with the numbers plugged in. So v naught t, and this, by the way, is where I'm going to write down my units and double check that my units make sense. I need to have the same units in every term, or else I've really messed up somewhere. So v naught t, which is 6 meters per second times 8 seconds, plus 1/2 times my acceleration, 2 meters per second squared, times time squared. Don't forget to square that time, or else your units aren't going to be right. Now I pick up my calculator. So 6 times 8 is 48, 1/2 times 2 is 1, 8 squared is 64. 48 plus 64 rounds off to 110. It's actually 112, but we only have 2 sig figs here, so that's going to be all that we need. Am I done? No, I am not. The last thing that we do is always the reality check. I have to ask myself, is my number reasonable based on physical circumstances? Is 100 meters a reasonable distance for a speedboat to go in 8 seconds? Well, I know that Olympic sprinters can do 100 meters in 10 seconds, so the boat can certainly go that far. It's probably not going too fast, but that's a very reasonable distance to travel in 8 seconds. So I think our answer is going to be good. Okay, so to recap the steps, write down the variables I know, pick the equation that has those variables in it, solve, plug in the numbers, get the answer, reality check. Let's do this one more time, and then that's the end of this video. Example 6. So given this diagram, find the displacement. We've got a jet that starts at 0, has a massive acceleration of 31 meters per second squared. Final velocity is 62. How far did it travel? All right. Always write down what variables I know. So I've got my initial velocity and my final velocity, acceleration, x equals question mark. Now I go look to my big 4 equations, find the equation that I want that relates all these 4 variables in it. So v squared is v naught squared plus 2ax. Now I need to solve this for x, so I'm just going to move the v naught squared to the other side, divide both sides by 2a, and I've got x is v squared minus v naught squared over 2a. I write down the equation for the last time with the numbers plugged in, and I always make sure to write down my units and check that the units work out. So I've got my final velocity, initial velocity over 2a, and I can see that meters per second quantity squared divided by meters per second squared still leaves me with 1 meters left over, so my units are okay. Now remember, I'm not done yet. I'm only done after I do my final reality check. I say, is 62 meters a reasonable length for, say, half of an aircraft carrier? Seems a little short, but the acceleration is huge. I'll have to accept it. If the answer I had gotten were 62 kilometers or 62 centimeters, I would think that would be crazy and something's gone really wrong. But 62 meters, I can accept. All right, so what have we done in this chapter? We've talked about some quantities like displacement, velocity, acceleration, and time. And then we use these in equations that will let us describe motion. So again, we don't know why things move yet, but we know how things move. There's also a section at the end of chapter 2 that talks about how gravity is constant acceleration, approximately, near the surface of Earth. And so we can use that to describe free fall. Now we're going to do a lot with that in chapter 3 when things start moving across the second dimension. But that's it for chapter 2. Thanks for watching.